The ACM A.M. Turing Award is the highest honor our profession bestows. It recognizes innovations that have significantly changed the entire practice of computing. Often referred to as the Nobel Prize in computing, the Turing Award includes a $1 million cash prize. This year, we were all delighted to learn that SC's very own Jack Dongarra received the Turing Award for his pioneering work in HPC.
For nearly 40 years, Moore's law has produced exponential growth in hardware performance. During that same time, while most software failed to keep pace with these hardware advances, high-performance numerical software did. Join us as we hear from Jack Dongarra, the 2021 ACM A.M. Turing Award recipient, for his pioneering contributions to numerical algorithms and libraries that enable high-performance computational software to keep pace with exponential hardware improvements for over 4 decades.
I'd like to think that I've had 3 major contributions to the field. The first one is in developing packages of mathematical software, in particular linear algebra software. What we've typically seen is computers changing over a decade in major ways. And these major ways have produced 3 orders of magnitude improvement in performance. And each architectural change really requires a rewrite, a redesign, restudying of how the algorithms are developed. It may require us to develop new methods, new algorithms to effectively use that architecture. One way to view it, perhaps is a crude way, hardware architects take their computer, throw it over the fence at us. We then have to design, look at that hardware, try to figure out what the best way to match our software and algorithms to that hardware. The second thing I'd like to say I've contributed to is the ability to develop MPI interface, message passing interface. So it was a community developed standard, de facto standard, which was put in place to provide a mechanism to allow for portable programs to be written, so I can run a program on one machine and take it easily to another parallel machine, perhaps by another vendor, and have that program run on that machine without any changes. And the third thing is this area of performance evaluation and benchmarking. While I was at Argonne National Laboratory working on a project called the LINPACK, we were writing that software package, and in the appendix to the user's guide for that software, I composed a table which measured the performance for solving a system of linear equations and doing it for a matrix of size 100. I had a colleague in Germany, Hans Moyer, who was at the University of Mannheim. He had a list of the fastest computers ranked by the theoretical peak performance. So Hans and I got together along with Eric Strohmeyer, and we put together this list of the 500 fastest computers, and we called it the Top 500. That was released, I think, in 1993. It comes out twice a year since then, and it's sort of an interesting way to measure and look at the performance changes over time. So it shows trends, it shows how things have evolved, it shows our fastest computer, which is the #1 computer, down to the machine that just made it onto the list. But the top 500 list is interesting. You know, the fastest computer back in 1993 was a computer at Los Alamos National Laboratory. It was a machine called Thinking Machines. And that Thinking Machine computer had 1,000 processors in it. Today, my laptop, the thing I use really to read email, is faster than that computer that was used for nuclear weapons simulations. So you could see the changes that have taken place in really a short period of time, and looking forward, we'll see major advances in the same way.
The standards Jack Dongarra helped create, such as MPI, the LINPACK benchmark, and the top 500 list of supercomputers, underpin computational tasks ranging from weather predictions to climate change to analyzing data from large-scale physics experiments.
I was a graduate student and I was working at Los Alamos National Laboratory. At that time, the Cray 1 was the supercomputer that Los Alamos had. In fact, the LINPACK benchmark is the thing that I was running there to try to capture how fast that computer was. Part of the test also involves checking to see if you got the right answer. And based on that check, I was getting the wrong answer. So of course I thought I had a bug in my program. So I spent the next few days trying to understand where I had gone wrong. So I finally had enough nerve to go up to one of the hardware guys and said, I'm getting the wrong results here, and I wonder if maybe the hardware can be making a mistake here. And in fact, the hardware was making a mistake in one of the computations with a certain exponent. It was giving the wrong results. And I think that's an important aspect. You know, we should have a sense of our solutions that we run on our computers, and a sense of how well those solutions match what we think the results should be. And without that kind of intuition, I think we could be in for a lot of problems. Trying to discover new ways of solving things, or new ways, faster ways, better ways, more accurate ways of solving problems. That's something that I think drives me in terms of the research I do, in terms of developing new algorithms and ultimately software that runs on a computer.
Learn more about the 2021 ACM A.M. Turing Award recipient, Jack Dongarra, in the June 2021 Communications of the ACM.
SC22 is privileged to host the official ACM A.M. Turing Lecture. As anyone knows who has come to SC, this conference really is unique. Its exhibitions include demonstrations from dozens of research institutions and hundreds of commercial enterprises, representing the full spectrum of high-performance infrastructure and services. SC is also unique because it brings together a truly amazing mix of people from universities, companies, government agencies, and research organizations, all of you in the room today. Many of us who work in HPC find ourselves relatively isolated in our own workplaces. There may be only a handful of people who use HPC. That means each year, SC provides us with our biggest opportunity to meet and learn from the rest of the HPC community. For today's Turing Lecture, Candy Culhane and her team asked Jack Dongarra to tell his story, because it is also the story of HPC and the story of SC. Starting with the very first SC conference in 1988, Jack has used SC to get feedback for his ideas, to jumpstart new collaborations, and to share his amazing results. His story also shows the remarkable impact that a single individual can have by finding and partnering with collaborators from other organizations, other fields, and even other continents. Speaking on behalf of the SC leadership team, I hope hearing Jack's story will give you new ideas and encourage you to find some exciting new collaborations this week. Please join me in welcoming Jack Dongarra to the SC22 stage.
I wasn't expecting this. Wow, that's quite an introduction there. Wow, I've never had that. Well, welcome. Hello, SC22. It's so great to be here with you in Dallas and in person. You know, this is really HPC homecoming for us, and it's really terrific to be here in person. I have to say it's a tremendous honor to be the most recent recipient of the ACM Turing Award. And an award like this couldn't have come about without the help and support of many people over time. And I want to just give a shout out to my mentors, colleagues, generations of postdocs, students, friends, my staff at the University of Tennessee who pushed things in the right direction to receive this distinction. I'm incredibly proud of the numerical software libraries that were created, the standards that were put in place, and the performance development tools that we deployed. I feel that this award is a recognition by the computer science community of the importance of HPC in computing and our collective contributions to computer science as well. So congratulations to us for making that happen. And with that, I'd like to start. So I'm going to tell you a story about my family. I haven't told many people this story, but my grandparents, all of my grandparents, as well as my father, were born in Sicily. My grandparents come from two small villages in the center of Sicily, one called Villa Rosa and the other called Santa Caterina. I had the opportunity to go visit those places. You know, it's mountainous, it's rocky, there's a sense of isolation in these very small towns, villages. My grandfather actually worked in a sulfur mine while he was there. And they decided to leave. My grandfather was 42 when he took the family, went to Naples, boarded a boat, and sailed for Ellis Island, and that was in 1929. He had $25 in his pocket, and you know, filled with hopes and dreams of a life there. My father, he was 10 years old, so this is his immigration card when he left, and this is his medical record saying he was safe to make the journey. My parents, they had very basic education. In fact, they didn't complete high school. They didn't go to high school. They did understand the importance of education, of college, and they did understand about working hard and being good role models for that. All throughout elementary school, as well as high school, I did pretty good in math and science, but I really struggled with reading and spelling. And later, as an adult, I learned I am dyslexic. I wanted to be a high school teacher. I went to a place in Chicago where I grew up that was the place where they educated the teachers for the Chicago public school system. So that was my dream, to be a high school teacher. My last semester in college, I was encouraged to apply for a position at Argonne National Laboratory. And this was a position where you would spend a semester with a scientist. And I was selected for the program. I think I joined about 30 other undergraduates at Argonne working. I was in the math and computer science division at Argonne, working with Brian Smith on software for mathematical software. And it was a transformational semester when I was there. I realized I had a passion for that kind of those kind of things, that is developing software, mathematical software, and linear algebra as a result of that encounter. I stayed at Argonne from that point until 1989. But the high-performance systems, when I started, were these two machines. A CDC 7600, that was a machine that had very limited memory, 64 kilowords of memory. It was Seymour Cray's design. It had a peak performance of 36 megaflops. At Argonne, we had the other major high-performance machine, and that was an IBM 370 195 system. It had about 4 megabytes of memory and had a peak performance of 55 megaflops. Those machines were scalar, of course, but they had a high degree of pipelining and instruction-level parallelism that was capable in those machines. there was a need for software, mathematical software, linear algebra software. The leader in the field of linear algebra is Jim Wilkinson. So Jim was a quite interesting individual. He actually worked with Alan Turing. He worked with Alan on the Pilot ACE project at the National Physical Laboratory just outside of London. And Jim actually won, or was awarded, a Turing Prize in 1970 for his contributions, his insights into backward error analysis. So Jim was the leader. He and Christian Reinsch produced a book which contained the state-of-the-art algorithms in linear algebra, mainly for solving eigenvalue problems. And at Argonne, we had a group spun up to do work to take those algorithms and to realize them in Fortran. So it was an effort not only at Argonne, but at other places as well. So as you can see from the authors of this book, it's a handbook for solving eigenvalue problems. It's called the Ice Pack Guide. Brian Smith was the lead in terms of the architect for it, but other people at Argonne, as well as my colleague Cleve Moeller, was involved in that project. That's where I first met Cleve. It was during this project here. This project was basically a project to translate the algorithms that Wilkinson and his colleagues had put together, the state-of-the-art algorithms, translate them into Fortran. So that was our task, and to do that so that the resulting Fortran programs would be portable. That is, we would be able to take them from one architecture to another without major changes. That seems like a trivial thing today, but at the time, we didn't have IEEE arithmetic. In fact, each manufacturer had their own way of doing computations, their own word size, and it led to many issues, especially when algorithms need to iterate and converge to a specific accuracy. But that was the task. It was a very successful project. It did a very faithful translation of the ALGOL into Fortran. If you know something about ALGOL, ALGOL is organized by rows. That is, the matrix two-dimensional arrays are organized by rows. And the translation was done into Fortran. And if you know something about Fortran, Fortran organizes it just the opposite by columns. But we did a faithful translation, and the result of that had significant impact in terms of the performance that we saw from those algorithms. Well, in the 70s, vector computers were the thing. The Cray 1, of course, is a classic vector computer. It had high peak performance of 120 megaflops. It had vector registers, so it had the ability to store vectors that were streamed from memory into these registers. Think of them as a cache. There were 8 of these vector registers, 64 elements, and we could operate from that. There was a competitor to the machine called the CDC Star 100. It was also a vector architecture, but the vectors in this case were streamed from memory into the computational unit, and the results were streamed back out to memory. So there was no way to store or cache those vectors, and that had a tremendous impact in terms of performance. Where the peak performance of the machines were similar, the actual performance one saw from running on them highlighted the benefits of having those vector registers in the Cray 1 system. So, we were evolving our ideas about software, trying to match the hardware characteristics of the time. So the hardware characteristics were vectors, so we thought we should put in place ideas that highlighted those vector operations. So there was a de facto standard, community-based standard that was proposed by 4 people, Chuck Lawson, Fred Crow, David Kincaid, and I'm missing the last one, and Dick Hansen. Thank you, Cleve. And they proposed the standard for doing these vector operations. I had I went off and immediately implemented them in Fortran and used a technique of unrolling the loops. So that's a standard technique that we assume a compiler can do, but back in 1973, that was a rather novel thing to do, and that resulted in my first publication, Unrolling Loops in Fortran.
And it led to an improvement in performance about 10 to 20% on many systems. And the ideas were evolving. We wanted to take all the concepts and the opportunities for doing parallel, or not parallel, but portable programming that were gained in the IcePack project and move them into another thing, solving systems of linear equations. So the eigenvalue problem was one of the first things that was tackled, and the follow-on project was going to do systems of linear equations, least squares problems, and singular values. And this project would respect the Fortran organization, use this standard that was this de facto standard that was just put in place to accomplish that. And that's really the origins of the LinPack project. So LinPack, many people think of it as a benchmark, but it's actually a collection of software for solving systems of linear equations. It was funded by NSF. It involved 4 groups, one at Argonne that was contributed by myself, the University of New Mexico, that was Cleve Moeller, University of Maryland, that was Pete Stewart, and University of California, San Diego, that was Jim Bunch. So that's a picture of us. Jim Bunch is on the far right here, Pete Stewart, Cleve Moeller, and that's the 1979 version of me with a little bit more hair. And that's my car. That's my car with the LinPack license plate that we took. Okay, so in the appendix of this user's guide, I put together a little table, and in that table was a result of solving a system of equations for a matrix of size 100. And it reported on 24 machines ranging from a Cray 1 to a PDP, PDP-10, a DEC PDP-10 computer. So this table here is a record of that benchmark, if you will, solving a system of linear equations. I put down the time it took to solve it, and then the hand scribble is the rate of execution for each of those machines. So the Cray at NCAR turned out to be the fastest computer, and it's at 14 megaflops for solving that system of linear equations. And the guy at the bottom of the list is a PDP system that was at Yale. So that's really the origins of the LinPack benchmark. This is the first ranking of it. The top 500 hasn't even been thought of at this point in time. But I maintained this list, and this list grew from 24 machines to 100 machines, to 1,000 machines, to about 5,000 systems at one point. So there were many machines there, and we had a good basis for looking at performance. In the 90s, we had the attack of the killer micros. So we had cache-based systems, shared memory machines, machines which had a shared pool of memory that could be accessed by any of the processors. And a number of companies sprang up to build systems like that. So we had machines from Multiflow and Alliant and Convex and Kendall Square and others, all based on this kind of architecture. It was an exciting time to be involved in computing, to get our hands on these mini supercomputers and experiment with it. But all of these companies, of course, faded away quickly, couldn't sustain a business, and moved on or out. But there was a tremendous amount of knowledge that was gained during this time. In terms of the software that was being developed, because the machines had cache, we realized that we needed to raise the level of granularity of the operations. Vector operations were too simple. We wanted to exploit the cache as much as possible. So we got together a community activity to define what we called the level 2 and level 3 BLAs. Level 2 BLAs are matrix vector operations, and level 3 do matrix operations. And the idea being that we could store part of that data in the cache and get very rapid access to the elements of the matrices, and the performance would be enhanced as a result of that exploiting of that characteristics. And we decided to form an effort to develop software. This project was funded mainly by the National Science Foundation and the Department of Energy. It was to take the ideas and algorithms in LINPACK together with the algorithms and ideas in IcePack and put them together in a single package using those BLAS routines to build up the infrastructure. So this group of people here are the contributors. Myself and Jim Dummel were the major architects, and a group of people, including people from NAG and other universities, joined in that effort to design that software. So that's the LAPACK story. That's how it came about, using those higher level operations. At the turn of the century, the architectures continued to evolve. We had machines now that were distributed memory machines. So we had processors, and those processors had its own memory. And in order to communicate or pass data from one point to another, we had to engage in a message passing paradigm to do that communication. A number of companies were formed based on this architecture. We had companies like BBN, Miranet, Mirius, Thinking Machines, Intel, Masspar, N-Cubed, all designing machines based on this strategy. Message passing was in the air. We didn't have a standard. Each manufacturer had their own way of doing message passing. Each group had their own way of doing it. The group at Argonne had P4. The guys in the mountains of Tennessee had PVM. There was a group at Caltech that had its way of doing business. Another group out in Germany had their way. There was guys at Yale doing something else. So there was really a need to have a standard so that we can develop software that would be effective and be portable across the machines without having to make major rewrites of the software. And that really was the catalyst for MPI. So MPI was a community effort. It was started by perhaps 35, 40 people. It was bringing people together. We followed the roadmap that Ken Kennedy had laid out using the same template that he had for the HPF forum, High Performance Fortran Forum. And the idea was to bring together that group of people every 6 weeks and do that for 3 days, concentrating on developing a standard. And at the end of some period, the outcome would be the standard. We decided that around 1.5 years would be the right time, so that was a target. And we had great contributions from many people. The guys at Argonne, Bill Grupp and Rusty Lusk, they decided to do an implementation of the standard as it was being developed. So we had a way to test out ideas immediately, and that caused a terrific feedback that allowed us to make changes and ultimately ended up with having the standard implemented and easily being adopted by many groups. And that, I guess, is the origins of MPI-CH through the efforts of Bill and Rusty. So that was a good story. We had the basis for doing message passing. It was, again, based on a community effort. What we decided to do was to take that LAPACK software that was designed for shared memory and very simple parallel processing that would be encapsulated into those level 3 BLAs. We would rewrite the code using MPI, refactor the code to do data distribution, and ending up with an implementation that could be used on distributed memory machines. And that resulted in ScalaPack, which is the distributed memory implementation of the LAPACK efforts. So again, a software design being instigated by the needs of hardware changes that had taken place over time. So as things progressed, we see the architectures changing once again from simple message passing systems to systems which had multi-core, many core, together with hybrid architectures using accelerators to boost the performance. So we had the ability now to accelerate in a very unusual way the performance, floating point performance of our algorithms. And we set about to investigate how we can effectively use that architecture. So we had 2 experimental projects, I'll say, one based on using many core, and that's the plasma package that exploited that, solving systems of equations and eigenvalue problems that targeted many core, and another package called Magma, which really focused on accelerators and trying to express those linear algebra algorithms that would leverage the accelerators, the GPUs that were available on many systems at that point. So those were experimental projects that had a life. We were seeing machines now that had many, many processes. So we've seen machines that have tens of thousands of processes, and you know, our common way of programming those machines, a fork join, a bulk synchronous processing, was not going to work with this level of parallelism. So we had to come up with a mechanism that would overcome that fork join parallel processing, and we were able to reach in our bag of computer science techniques and decided that we would look at exploiting a directed acyclic graph. So the nodes in the graph represent tasks, computational tasks that would be performed, and the arcs represent dependencies between those tasks that would be scheduled in some way by a runtime system that would allow that to run effectively on larger numbers of processors. The idea being that if we could find the critical path in that DAG, we would release the maximum amount of parallelism that we would have. And in addition to looking at that model of computing, we also realized there was a need for doing batched operations. So we saw that in many of the algorithms, we had the same kind of operation being done on different data. So think about thousands of matrix multiplies being done. What we wanted to do is not have that run in a loop, but to have that as one call that would invoke those thousands of matrix multiplies, or thousands of singular value decompositions, or thousands of operations that would be done. That has a tremendous impact today in terms of many of the machine learning algorithms that are put in place. So the story continues in that way, where we have these standards. The runtime system that we employed at the University of Tennessee is called Parsec. It's similar to systems that many other people are engaged in. Legion is another example, StarPU in France, and the OMPSS in Barcelona are examples of systems that are able to manage a runtime and take care of that directed acyclic graph and schedule it appropriately across the rest. So as the architectures change, in the more recent times, we see architectures which are hybrid in nature. So we have systems that are being built on many core and using multiple GPUs for a node. And an example of that is the Oak Ridge Summit computer. It has, on a node, it has 2 IBM Power 9 processors with 22 cores each, and it has 6 GPUs on that node that can be used to accelerate the performance. The interesting thing about this machine is that you had better be using those GPUs because most of the performance is coming from the GPUs. 97, 98% of the performance is going to be achieved by using the GPUs. So if you have something which just uses the CPUs, you'll be getting very inferior performance overall. So we've seen many changes take place over the past 50 years in terms of the software. Today we're working on a package called Slate. Slate is designed for exascale computing, trying to put together all the concepts and ideas that were developed over the last 50 years in terms of being able to have things that can effectively compute things with high accuracy, that have community involvement, that have the state-of-the-art algorithms put into it, that have the ability to achieve high performance, productivity for the user, being able to have readability, and also reliability of the underlying algorithms. So that's sort of where we are at the moment. And the software is intended to run on this pyramid of high-performance computing devices. At the bottom, we have maybe laptops. Going up, we have regional centers, and up to the high-performance machines themselves. So the idea is that that software could be run on that collection of machines without any changes from the user. The software itself would be able to adapt to the underlying architecture and get the maximum amount of performance that could be exploited from that. So that's what the Slate software is intended to accomplish. So today's environment for developing numerical libraries is highly parallel. It uses distributed memory. There's a MPI and OpenMP programming model. It's heterogeneous, using commodity processors and accelerators. It exploits things that avoids simple loop-level parallelism and tries to focus on looking at a directed acyclic graph for the computation. The thing to point out is that communication is tremendously expensive on these machines. These machines are over-provisioned for floating point, and the communication is really where we're spending most of the time, and that has to be taken into account in designing algorithms. My colleague Jim Demmel sort of cornered the market on the phrase and coming up with communication avoiding algorithms that can effectively deal with that. And that really says something about our conventional wisdom in terms of programming these things. So the conventional wisdom would say that if we have two algorithms that are going to be, we're going to decide between two algorithms to use on a machine, one algorithm does more floating point arithmetic than the other algorithm, the conventional wisdom would say we would choose the algorithm that does less floating point arithmetic. But because these machines are over-provisioned, and really it's communication that we're paying for, we really should look deeper and not just focus on the floating point operations, but look at what kind of communication is going on these methods. And the other thing that we have to realize is that 64-bit computations is what we commonly think of, but our machines today are capable of 32-bit, 16-bit, and even 8-bit floating point operations. And we should be looking at ways to leverage that increased performance by using this mixture, perhaps, of floating point arithmetic in our computations. And there's been some pretty good success stories in the linear algebra domain where we're able to leverage those and get considerable enhancements in performance itself. Well, I mentioned something about the top 500, about Horst, Eric, about Hans, Eric, and Horst Simon joined the group a little bit after it got launched. I've maintained the LINPACK benchmark for many years, since 1978. I had this list of thousands of machines for solving systems of equations. Hans and Eric had a list of the fastest computers, and he ranked those machines by the theoretical peak performance. Hans and Eric approached me and said we should really merge our two lists and call it the top 500. And that was the origins of that. And that happened around 1993. We're coming up to 30 years of the top 500. There's a BOF tonight right here that'll discuss the top 500 in a lot more detail. So this list is maintained. It's done twice a year. It's updated twice a year. It's updated here, and also the machine that's held in Germany. It'll be held in Hamburg in June or May or June of the year. So the way to think of this is we're going to solve a system of equations. The ground rules say you must use Gaussian elimination with partial pivoting. You have to do 64-bit computations. And we're going to look at the performance. And typically, as you increase the size of the problem, the performance goes up until it reaches some asymptotic point. And what we'd like to do is capture the asymptotic performance for solving a system of equations using Gaussian elimination and 64-bit floating point arithmetic. So that's the basis for it. All the numbers we have since this list was created is based on those ground rules, and it presents sort of a snapshot, if you will, of high-performance computing over time. So this is something that Eric is going to talk about tonight, but I'll give you a glimpse of a little bit about what we have in store. So this table here is basically charting high-performance computing since 1993. So we're looking at the performance for the LINPACK benchmark since then. The guy at the top here in red is the #1 machine. So that's at 1.1 exaflops today. That's the Frontier system at Oak Ridge. The guy at the bottom of the list, number 500, is at 1.73 petaflops. So that sort of brackets, if you will, high-performance computing. So if you have a supercomputer, you should be somewhere in this bracket, I would say. If you're not in there, you probably don't have a supercomputer, is one way of thinking of that. So this list goes back. You can see what's happened back here in 1993. We got 60 gigaflops was the fastest computer, and the machine that just made it on the list back then was 422 megaflops. So just looking at this, you know, the number one machine back in 1993 was that thinking machines at 60 gigaflops. And you know, the laptop that I normally use to give presentations and look at email is something I can run the benchmark on. So it's an Apple Air with an M2 processor, and when I run it, I get 426 gigaflops out of my laptop. That's a stunning achievement, my goodness. You know, that's of course faster than the fastest machine back in 1994, and that mark there, what my laptop is getting, is what the number one system was in 1993, which was a machine at the University of Tsukuba, which was a Hitachi-based system. So incredible changes taking place over a very short period of time, giving rise to that. So this is the top 10 list. Again, Eric is going to talk about this a lot more detail. So this is the 10 fastest supercomputers. The way to read this is, this machine is number one, the machine at Oak Ridge National Laboratory. It's a Department of Energy laboratory run by the Office of Science. It's the Frontier system. It has integrated by HPE, has an AMD processor and some AMD GPUs as well, and it uses a Cray slingshot interconnect. It has 7.7 million cores in it. So if you're going to use this machine at scale, which it's intended to be used at scale, you have to manage that 7.7 million core count. The peak performance for the benchmark is at 1.1 exaflops, and that achieves 65% of the theoretical peak. So the theoretical peak is a paper and pencil calculation, right? You look at the cycle time, how many processors you have, what the potential is, and that gives you the theoretical peak. The machine consumes under load 21.1 megawatts. So what's a megawatt? So if I use a megawatt at my home for 1 year, I'm going to get a bill for about $1 million from the electric company. So a megawatt year is $1 million. So $21 million, at least in Tennessee, that's what the cost is. And maybe prices may vary. Perhaps in Japan, they're a little bit more. The Fugaku system is the next guy. Again, very large machine, very high performance, but look at the difference between number one and number two. And you see the percent of peak and the power consumption. And this last column represents the efficiency, if you will. So you want a high number here, gigaflops per watt. So 52 is the highest, one of the highest ones on the list. I guess this guy here is a little bit higher. And this machine is the machine in Finland, Lumini. It's sort of the mini-me of the Frontier system. So it's a smaller version of the Frontier system. And you can look down the list. I've highlighted in orange here the machines that use accelerators. So on the top 10, they all use accelerators except Fugaku. So Fugaku is a machine which has vectors, I guess the only machine that uses strictly vectors on this list. And you know, a credit to the architecture there, it gets a very high percent of the theoretical peak performance. You know, we see 5 machines in the US, 1 in Japan, 1 in Finland, Italy, and a couple machines in China. The Chinese machines are interesting. This is a processor. The Sunway system uses their own processor, 260 cores, and this machine, the Tianhe 2A, is a machine which uses Intel parts plus an accelerator that was designed in China. And of course, China is going to have a hard time acquiring Western technology for their machines in the future. So that's the top 10. That's the top 10 list. So what's an exaflop? So a flop is an add or a multiply. That's the first thing. And we're talking about 64-bit operations here. And an exaflop is a billion floating point operations per second. A billion. I gave a talk a few weeks ago, and after my talk, I said that, and after my talk, I was interviewed by the newspaper guy, and I said, $1 billion, and he went off, and I looked at the newspaper the next day, and what appeared was 2 billion. This is not 2 billion. This is a billion operations. You know, this is lots of operations. So you know, think about an exaflop and think about everybody on Earth. Think about everybody doing 1 operation per second. It would take 4 years to do an exaflop, and that's what this computer can do in 1 second. So that's an incredible amount of computing power that we have in these machines today. Just incredible. So here's the breakdown in the top 500. This is going to be discussed later today. I just wanted to quickly give a glimpse. China has the most supercomputers. So it has 162 supercomputers of the 500. And the US has 125, and you can see the rest of the breakdown in that list. So they have the most supercomputers in China. Most supercomputers are in China. They also produce the most supercomputers. So China is the producer. They sell the most worldwide. And the main sellers are, or integrators, I guess is the right way to say that, are Lenovo, Sugan, Inspur, Huawei, and NUDT, which is the National University for Defense Technology. There's also rumor of 2 exascale machines in China. They haven't submitted the results, right? But we have pretty good evidence that those machines exist. They won a Gordon Bell Prize last year and exhibited high performance. They wrote up their architecture. We know exactly what the machines look like, and there's rumors that they ran the benchmark, but they haven't submitted it to us. So the way you get in the top 500 list is you run the benchmark, you email you send the output of the benchmark to the website, the top 500 website, and it gets registered from that point on. They haven't done that. So the question is, why haven't they done it? Why haven't they submitted the results? And I would guess it's geopolitical. They don't want to alarm the US even more than they're already alarmed and cause other problems to occur. Okay, so in the States, we have this exascale computing program. It costs, so we're designing exascale computers, we're designing applications and software. The cost is $4 billion, and that's over 7 years. We're in year 6 of that project. We just finished year 6. We're starting the 7th year of this project. So what do you get for $4 billion? Well, you get 3 computers. There's 1 computer in place at Oak Ridge. That costs $600 million. There's a machine that's being put in place at Argonne, maybe. And there's a sorry. I'm sorry. It was just too tempting. I'm sorry. And then there's another machine going into Livermore. In addition, we have $400 million in non-reoccurring engineering to help modify the architecture so it would fit better into our framework. There are 21 applications in the ECP project that have been targeted. Those are the real reason why ECP exists, is to do those applications. And you know, they all are energy related. They all have a big impact and hopefully will drive science forward. And there's a software stack as well. So there's 84 projects that people are engaged in to develop that will help with the applications run effectively on those machines. So that's the exascale computing project. And you know, when we look at performance today on our machines, the data movement is the thing that's the killer. So this graph here is Mark Gates at Tennessee put this graph together. It's sort of informative. We're looking at different processors, and here is the execution rate of the processor, the flops, and divided by the words that can be transferred from memory. So we're looking at the floating point execution rate divided by the data movement rate. And we're looking at different processors. In the old days, we had processors that basically had a match of 1 flop per 1 data movement. That's how they were balanced. And if you guys remember the old Cray 1s, you could do 2 floating point operations and 3 data movements, all simultaneously. So this is trying to get a handle on that. But over time, the processors have changed the balance. So what's happened over the course of the next 20 years from the beginning here is that an order of magnitude was lost. That is, we can now do 10 floating point operations for every data movement that we make. And more recently, we've seen that number grow to 100 floating point operations for every data movement. And even some machines today are in the 200 range. So that says there's a tremendous imbalance between the floating point and data movement. So we have tremendous floating point capability, over provision for floating point, but we don't have the mechanism for moving data very effectively around in our system. Okay, benchmarking. The LINPACK benchmark's been around for a long time, since the mid-70s, let's call it. You know, it's a way to measure things. It has a lot of positive features. It's easy to understand. It shows trends. You know, we use it for the top 500. But, you know, a lot's changed since 1979 in terms of the architectures. The LINPACK performance is no longer strongly correlated with what we see in many applications. And, you know, the LINPACK benchmark is really doing dense matrix computations, and that's not what many of the applications are doing. So designing a system that gives a very high number for LINPACK may not be a good thing in terms of looking at real applications. So we decided to, what are the machines used for? The machines are used to do simulation. There's many problems that are being tackled in that simulation space. They're usually doing modeling. The modeling revolves around solving a three-dimensional partial differential equation. There's a discretization that takes place of that differential equation. And that results in a sparse matrix. So the matrix is not dense, it's sparse. You still need to solve a system of linear equations, but it's quite different in its characteristics. And the result of that is maybe we need another benchmark. So this is a benchmark that Mike Carew and Peter Loschek at the University of Tennessee have helped put together. It's called HPCG. It runs a conjugate gradient benchmark. The data structures are sparse. It's modeling a three-dimensional partial differential equation. There's a 27-point stencil. There's some preconditioner that's used to help in converging and sort of complicating the overall iteration strategy. And the idea is to look at the performance that we achieve on this thing, which perhaps better reflects the performance. So this is the results of the HPCG benchmark. Again, come to the BOF tonight, and we'll talk a little bit more about that. Just giving you a glimpse. The number one computer is this machine that comes to us from Riken Fugaku system. It achieved, this is the LINPACK number, if you will, HPL, and this is what the HPCG number gets. So this is a number here which talks about the percent of peak. So this machine is getting 3% of the theoretical peak performance. Just looking down the list here, we see very little return in terms of peak performance. And the machines that we have here, the machines that give us the number one in terms of the LINPACK benchmark are getting 0.8% of the theoretical peak performance, 0.8%. So think about having a race car that goes 200 miles per hour and think about getting 2 miles per hour out of it. You're not going to be very happy with that race car. So, this is an indicator here that we have an imbalance of the hardware on problems that perhaps are important this machine will be used to solve. It'll be hard to effectively get the kinds of execution rates that we're talking about. Okay, we're coming to the conclusion here. The hardware is continuously changing. We go from scalar machines to vector to distributed memory to accelerated machines to mixed precision. There's been these three computer revolutions in some sense: high-performance computing, deep learning that we're in today, and edge and AI-based systems. We're in sort of a catch-up mode all the time, I feel. The architecture changes, and the algorithms and software tries to catch up with that architecture, with the hardware. I have this image of the hardware people throwing something over the fence, and the algorithms people and software guys scramble now to figure out how to fit their problems on that machine to effectively deal with it. And it takes about 10 years to do that, and then a new machine is thrown over the fence, and we start that cycle over again. So algorithms, there's plenty of room at the top. There's a great paper, I think, that was written not too long ago. This is a paper by Charles Leiserson and company. It appeared in Science 2 years ago, and the title is "There's Plenty of Room at the Top what will drive computer performance after Moore's law. It talks about many of the things that I've just rambled on about here. It's a riff, of course, on Feynman's classic lecture on There's Plenty of Room at the Bottom, talking about quantum stuff. So with that, I'm going to have to leave you. Let me just thank. I've got too many people to thank in person. So here's a list of people that have helped me in terms of get to where I am today. So thank you very much for your attention, and I'd be very happy to answer any questions that you might have.
Great job, Jack. Thank you so much for a really inspiring talk. We do have time for a couple of questions from the audience. If you're here in person, go up to one of the two mics in the aisles down here. They're back there? Okay, back there. And in the meantime, we've also had people who are attending SC virtually and have been able to submit their questions through the app. So I'm going to start by asking Lori Diashin, who is chair of the SC22 virtual program, to begin by reading the most upvoted remote question. Lori?
Thank you, Cherry. Jack, the most upvoted question was, what type of architectures do you expect to see in the coming years? And what are the challenges that you see in adopting those current benchmarks to maintain a top 500 list?
Right. So what's going to happen in the future for architectures, and what's going to result in terms of software infrastructure that supports it? So today we have machines that are built on many core plus GPUs. So I would think that in the future we would see that expand, not only many core and GPUs, but have other accelerators added to that collection. So think about adding an accelerator that does something specific for AI, or think about adding an accelerator which does something like neuromorphic computing. So we can add accelerators to the collection to help in solving our problems, and we could dial, maybe quantum would be another accelerator. I don't see quantum being its own computer. I see it being maybe an accelerator that we might add to the collection of accelerators that we have, so that specific applications could draw on those components to get high performance, or a user could dial up perhaps what mixture of accelerators they choose to have on their specific system according to the applications. So it's about making sure that we have the hardware matching the applications that are intended to run on this machine, and having the right mixture so it makes it easier to extract the performance and easier to develop the software for that ultimately, and having that mixture.
Thank you. So our next question, let's take one there.
Congratulations. Remind me of my CDC cyber and thinking machine experience. Thanks for the peony flower from your Turing Machine Award bouquet. You talk about 65% peak performance. Can you elaborate what that was? I forgot, because I only remember the 3 to 6% you talk about for the benchmark. And I'm trying to do load imbalancing self-organized static mapping from DAG to try to improve the 3 hops on Slingshot and Dragonfly to 0 to 1 hops. So hopefully they will try to reduce using static to complement the dynamic load balancing and scheduling. And so I was wondering, when do you think we're going to have execution on memory?
So I think you asked a few questions. I'll answer the ones I have good answers for. How's that? So you've said something about 65% of the performance. That was for Frontier. frontier is getting 65% of the theoretical peak. So think about a problem which is highly computationally intensive. Matrix multiply is really what the benchmark is, and we're only extracting 65% of the performance. And that says something about the interconnect. And it's highlighted even further by the 0.8% of the theoretical peak. So there's issues about moving data around in that machine, and where the issue is, I'm not really clear where the specific thing is, but it doesn't. It says that it's going to be hard to extract performance from that architecture.
What is the reason for 0.8 to 3%? Is that because not enough degree of parallelism?
So no, it's not the parallelism. It's the data communication. It's the bandwidth latency issues associated with that particular architecture on the algorithms that are being used.
Great. Have we got a question over there?
Hi, Andrew Chen from the University of Chicago and Argonne National Labs. First, Jack, congratulations on a
Thank you, Andrew.
Richly deserved. One of the opportunities in giving a Turing lecture is to take a bit of a forward-looking kind of perspective and either highlight areas that maybe you think are underinvested and you wish there was more research going on in those areas, or maybe highlight some directions you think are particularly important for the community to invest in, both our effort as well as perhaps funding in order to ensure a prosperous future. So I just wanted to tee up and give you an opportunity to maybe speak to a few things that you would recommend given your perspective.
Thank you, Andrew. That's a good question. So, I've harped on the imbalance of the machines and the machines. So today we build our machines based on commodity processors, commodity off-the-shelf processors from AMD or Intel, commodity off-the-shelf accelerators, commodity off-the-shelf interconnects. Those are commodity stuff. We're not designing our hardware to the specifics of the applications that are going to be used to drive them. So perhaps we should step back and have a closer look at how the architecture should interact with the applications, with the software. Co-design, something we talk about, but the reality is very little co-design takes place today with our hardware. And you can see from those numbers, there's very little that goes on. Perhaps a better indicator is what's happening in Japan, where they have much closer interactions with the architects, with the hardware people, to design machines that have a better balance. So if I was going to look at forward-looking research projects, I would say maybe we should spin up projects that look at architecture and have the architecture better reflected in the applications. There's going to be a panel that Dan Reed leads Wednesday, which is going to bring up this topic in detail. So if you're interested, come to the panel. I forgot where it is, but I'm sure it's listed in the book to see it. But I would say that we should have a better balance between the hardware and the applications and the software, really engage in co-design, have spin-up projects which look at hardware. In the old days, when I was going to school, we had universities that were developing architectures that would put together machines. Illinois was a good example of that. Stanford, MIT, CMU, other places spun up and had hardware projects that were investigating architectures. We don't see that as much today. Maybe we should think about investing there, putting some research money, perhaps from the Department of Energy, into that mechanism for doing that kind of work. So that's my take on that.
Great.
Thank you.
Let's go to Lori and another remote question next.
Okay, great. The next question is, with software and algorithms being adapted to accommodate all the different architectures that you've described, the question is, how do we think about maintaining provenance and guaranteeing reproducible results?
And guaranteeing reproducible results. Okay, yeah. So this is an important issue. It's always an important issue. It comes about. It's more topical today to talk about this. We need ways to verify that we are getting a result that makes sense first. We need to the story I told earlier about this Cray machine. and getting the wrong answer. That's a good indicator here. We should have a sense of what the answers are. In the case of the benchmark, we have a mechanism for checking to see we got the right answer, so we can easily verify that we've got that. But we should all have a sense of what the answers look like, so that we can not just accept the answer that comes out of a computer and move on to the next thing. So that's one thing. The other thing is we should have mechanisms so that we can, in fact, reproduce results, have a mechanism that describes the algorithms in enough detail that somebody else can pick that up, move it to another machine, and run that on a machine and get the results. I would say that should be part of our strategy for doing any kind of science, being able to reproduce the results that we have and do it in a way that other people can easily accommodate for that. But I don't have a magic silver bullet to do it.
We'll take one back here.
Here's one of my colleagues, a perennial, I see him.
You know, when I met you in '76, you had a lot of hair.
I did have a lot of
and I never knew you were so bald because you always wear hats.
I don't always, but okay. Yes, I'm not wearing one now. That's right. So John and I go back a long way. I think I first met you on a flight from Albuquerque to Los Alamos.
That's right.
That's right, yeah.
So my question is, we used to have meetings, I think it was in the 80s, where it was determined that we would never, ever get to, I think it was a petaflop. and I mean, here we are at a couple exaflops. And so what were we, I mean, the brightest people around were at those meetings. What were we missing?
Okay, so what happened? How did we get past that? It's impossible to do it, and how do we move through that? So we had a number of architectural changes. GPUs are an example of something that changed the landscape, made things more effective in terms of being able to get the performance. So I look back. I think it was 1987. We were at a teraflop. So the ASCII red machine at Sandia was a teraflop. 1987. 11 years later, we were at the petaflop with the Roadrunner, and then 14 years later, so 3 orders of magnitude, 14 years later, another 3 orders of magnitude came about with the Frontier system. So that's where we are today at exaflop, and now maybe a question could be, when do we get to 3 orders of magnitude again? So zettaflop, when are we going to get there? And I would say, you should come to the BOF, come to the BOF tonight. So one of the projections says it's going to take another 8 years just to get 1 order of magnitude. So just 10 exaflop, the projection would say that. But come to the BOF tonight, and we'll unveil more about that.
Next question, please.
Hi, and my name is Chun Hua Liao from Northern Livermore. And so my question may be a little bit off topic. And I think HPC is driven by many wonderful applications that have like a huge impact. But right now, I think there are many kind of high impact problems that may not be addressed by our community. For example, our nation is polarized between 2 parties. And we have elections that happened after 1 week, but still not finished the counting. While we are talking about billions of billions times the machine can count. So I'm not sure what's your comment about our community, how to address the big elephants in the room, those kind of problems. Thank you.
Wow, okay. I think we're out of time.
We are actually running very short of time. And that's not a question with an easy answer. So I would suggest we take that one offline with Jack. And for those of you who still have questions, you know what he looks like. He's always wandering the halls or in a session. So grab him and give him your questions. But thank you, Jack, and let's thank and congratulate Jack once again.
You guys are too much.
Thank you. Thank you to everyone who attended this inspiring Turing lecture, and especially to our honored speaker, Turing laureate Jack Dongarra. I invite you now to go and enjoy your time at SC22, where you will see the many ways that HPC accelerates.